In this video, we're going to look at variable transformations used for second-order linear PDEs. The main idea of this video is that by using a particular type of linear transformation of independent variables, we can transform a PDE into an equivalent PDE whose solution as a function of the transformed variables allows us to readily define a function in terms of the original variables that solves the original PDE. We're also going to classify second-order linear PDEs as elliptic, parabolic, or hyperbolic. The first concept we'll need is that of a coefficient matrix. If you have a second-order linear PDE with unknown function u, we can form a matrix A that holds the coefficients of all second-order terms appearing in the PDE. We can also form a vector C to hold the coefficients of the first-order terms in the PDE. As an example, if we have this PDE, the coefficient matrix is the 2x2 matrix shown here. If we assume that we can exchange the order of differentiation, it's sufficient to always consider a symmetric coefficient matrix. The reason coefficient matrices and vectors are useful is because they change in a predictable way under a linear transformation of independent variables, whereas you'll see in a minute, we represent said linear transformation by a matrix. As an example of what we mean by linear transformation of independent variables, let's look at a first-order PDE with coefficient vector 1, -1. The independent variables are x1 and x2. We can define a transformation of independent variables by setting a new variable y1 equal to x1 plus x2 and a new variable y2 equal to x2, which is represented in matrix form seen here. This is the transformation we get by assuming the columns of B inverse to be our new basis vectors for the y1, y2 coordinate system to describe 2-space. Because this transformation is invertible, if the original PDE had a solution, that is a mapping from R2 to R in terms of the original coordinates x1, x2, we can define a new mapping from R2 to R, the new u function that has the same output at its input y1, y2 as original mapping u had at the input x1, x2, where x1, x2 is a coordinate point input that corresponds to input y1, y2 under our transformation. This is what we mean when we say the function u in y1, y2 coordinates. It's not technically the same mathematical object, as considered as a mapping from R2 to R, they generally will not be the same and shouldn't be the same, but it is the same function of underlying space. To make our lives easier, when context makes it clear, we'll refer to both the original and transformed unknown function by u. Now, since the transformed function is not the same mapping from R2 to R as the original one, it'll likely satisfy a different PDE in terms of its independent variables. The PDE the transformed function has to satisfy, in order for the untransformed function to satisfy the original PDE, is what we call the transformed PDE. And if our variable transformation is invertible, solving one gives us a solution to the other. Let's actually work through an example now. The key fact to remember is the definition of our transformed function. It's the function such that when evaluated at the new coordinate pair, that corresponds to original coordinate pair x1, x2, equals the original function u evaluated at x1, x2. In this case, our transformation is that y1 equals x1 plus x2 and y2 equals x2. We've now written our original function as our transformed function composed with the transformation function of our original independent variables. So when we plug it into the PDE and simplify it by differentiating, the multivariable chain rule pops out a few derivatives with respect to the transformed variables y1 and y2, which is exactly what we want. The derivatives of the transformed variables with respect to the original variables are easy to find and come directly from the transformation matrix B. Plugging them in, we can simplify to the following, which simplifies further to negative u sub y2 equals 0, which is a much simpler PDE than our original one. Notice that this PDE is easy to solve. The solution is just f of y1 for an arbitrary function f. Remembering how our original function is defined in terms of a composition of the transformed function, this tells us that the general solution to our original PDE is an arbitrary function of the sum of x1 and x2. Interestingly, notice that the coefficient vector for our transformed PDE is just b times the original coefficient vector, where b is our transformation matrix. Next, let's look at the general case of a first-order PDE with coefficient vectors c. Once again, the transformed function evaluated at bx equals the original function, where x is the vector of independent variables input to u, and b is an invertible matrix. Once again, we plug in this form that we've written the original u function into our original PDE and differentiate applying the multivariable chain rule. Remember that we can write each of our new variables as a linear combination of original variables with coefficients taken from the B matrix. This lets us simplify to the following. It's not quite in the form that we want if we want to readily observe the coefficient vector from the PDE, because each of the summands here have various different derivatives of u. But if we gather like terms with the same y derivative, we end up getting that the kth entry of the new coefficient vector is the following sum, which turns out to be nothing other than the kth element of the vector b times c. Therefore, the coefficient vector of the transformed PDE is just b times the coefficient vector of the original PDE. Knowing this, you can sometimes work backwards and find a b that will give you a coefficient vector that you can more easily solve than your original coefficient vector. Moving on, let's look at the case of a second-order PDE. We'll keep the coefficients on the second-order derivative terms in the matrix A, and we'll keep the coefficients on the first-order terms in the vector C, and we'll keep the coefficient on the unknown function itself as a single number d. Next, consider the transformation y equals bx, where b is an invertible n by n matrix. A useful symbolic statement will be the sum that appears here, which just comes from the definition of matrix vector multiplication. Once again, the transformed PDE is defined to be the PDE we arrive at by the following process. We substitute the unknown function, u nu of bx, for the unknown u in our PDE, and then we apply the chain rule to get a new PDE in terms of the new function and its derivatives with respect to the new independent variables. It's our assumption that b is invertible, together with the process that we use to construct this PDE, that ensures we can get a solution to our original PDE. Before we get into the theory of transforming a second-order PDE, let's do an example. Consider the following second-order PDE, with its coefficient matrix is shown at the top of the screen, together with a definition of our transformation for this example. Using substitution, we get the following. We should now find all derivatives that appear in the PDE. If we use the chain rule, we get the following expression when we differentiate our composition with respect to one of the original independent variables. We can simplify derivatives of the new independent variables with respect to the original independent variables using the coefficients of b. We've now used the expression in red and the entries in b to find all derivatives that appear in the PDE. Substituting them into the PDE, we get the following. It simplifies to a wave equation, which we can solve more directly than our original PDE. Notice the coefficient matrix of our new PDE is a similarity transformation under b of our original coefficient matrix A. This will be true in general and a very useful fact. Let's move on to the general case of a second-order PDE with no first-order terms or lower, written as a sum set equal to 0. It has coefficient matrix A, and let's consider an arbitrary invertible transformation matrix B. As usual, let's substitute the composition of the transformed function with the transformation into our original PDE. To simplify this, remember that we can write the transformed function differentiated with respect to one of the original independent variables as a sum, thanks to the multivariable chain rule, where the coefficients in the sum are again taken from the matrix B. This is our expression for our first derivative. To take a general second derivative, we'll end up with a double sum by applying the chain rule and simplifying. We can plug this into the second line from the top of the screen to get the following in red. We still haven't gathered like terms, that is, terms with the same y derivative. To do that, notice that u sub yl yk appears once in our red sum for each index ij in the outer part of the sum, which means the coefficient on u sub yl yk, after gathering like terms, has to be as follows. Simplifying, we get that this is nothing other than the kth entry of the matrix B, A, B transpose. Since L and K were arbitrary, we can now say that the coefficient matrix A prime of the transformed PDE equals B, A, B transpose. It's straightforward to see that we can apply the results from earlier separately to arrive at the transformed PDE, which will have transformed coefficient matrix and transformed coefficient vector. Notice that if we assume we can exchange the order of differentiation, then we can always rewrite our PDE to have a symmetric coefficient matrix, which motivates the following definition. We say a PDE is hyperbolic if the following quantity is greater than 0. An example of such an equation is the wave equation. We say a PDE is parabolic if that same quantity equals 0. An example of this is the heat equation. We say the PDE is elliptic if the quantity is less than 0. An example of this is the Laplace equation. Here's where variable transformations come in handy. If we have a second-order linear PDE with two independent variables, as shown here, we can define the discriminant of the PDE to be b squared minus ac. Depending on whether the discriminant is greater than 0, equal to 0, or less than 0, we can transform the PDE into a wave, heat, or Laplace equation, respectively. Before we see why this is, let M be the coefficient matrix of our general PDE with two independent variables. Notice the determinant of M is AC minus B squared, which is just the negative of the discriminant of our PDE. So if the discriminant is positive, the determinant of M is non-zero and negative, which means M has two non-zero eigenvalues of opposite signs, by the fact that the determinant equals the product of eigenvalues. Next, if b squared minus ac equals 0, then the determinant of M equals 0, so it must have a 0 eigenvalue. Also, because we're assuming M is not the matrix of all zeros, it has to have some other non-zero eigenvalue. Finally, if b squared minus ac is less than 0, the determinant of M is greater than 0, so it has two non-zero eigenvalues, and by reasons similar to what we used above, the eigenvalues have to have the same sign. Now here's why the eigenvalues, combined with what we already know about variable transformations, are useful. From linear algebra, we have that for any symmetric matrix M, there exists an orthogonal matrix B such that B transpose equals D, where D is a diagonal matrix whose diagonal entries are the eigenvalues of M. We know something about the eigenvalues of hyperbolic, parabolic, and elliptic PDEs coefficient matrices, and with our fact from linear algebra, we can say that if a PDE is hyperbolic, then there's a matrix B such that B transpose is the following diagonal matrix. Similarly, if the PDE is parabolic, then there's a matrix B such that B transpose is this diagonal matrix. Finally, if our PDE is elliptic, there's a matrix B such that BM transpose is this diagonal matrix. And if you remember how a variable transformation Bx equals y changes the coefficient matrix of a PDE, we're basically saying that each of these types of PDEs can be transformed into a PDE with a diagonal coefficient matrix of the forms shown on this slide, which is useful because diagonal coefficient matrix PDEs are what we usually first learn to solve. As an example of this, for the hyperbolic PDE, we transform into the following, which just means that the second-order terms can be made to be like those of the wave equation. And the parabolic PDE transforms so that the second-order terms are like those of the heat equation. Finally, if we have an elliptic PDE, we can transform it so that the second-order terms are like those of the Laplace equation. Now let's consider a general second-order PDE, where after assuming we can exchange the order of differentiation, we've made symmetric the coefficient matrix, which we'll call A. Since we're now dealing with n independent variables, our old way of classifying PDEs into hyperbolic, parabolic, or elliptic doesn't apply anymore. But if you remember what our classifications resulted in terms of the eigenvalues of the coefficient matrix, we can extend our definitions to the case with n independent variables if we describe these categories using eigenvalues instead. We say that a PDE is hyperbolic if one eigenvalue has the opposite sign from the rest and all of them are non-zero. We say a PDE is parabolic if one eigenvalue is 0 and the others have the same sign. We say a PDE is elliptic if all eigenvalues are non-zero and have the same sign. From linear algebra, we again know that there's an orthogonal matrix B such that B transpose equals the diagonal matrix D that holds the eigenvalues of A. This means there's a linear transformation of variables produced by the matrix B that will transform our PDE to have second-order coefficient matrix D. Recalling that the diagonal entries of D are lambda sub 1 through lambda sub n, we get that a hyperbolic PDE assumes the following form after transformation. And we get the following forms after transformation for parabolic and elliptic PDEs. That's pretty much everything we're going to cover in this video. But you might be wondering what happens if our coefficients are time variable. In that case, our coefficient matrix will also be time variable, so its eigenvalues will vary with time, which means the classification of our PDE will also vary over time. To finish the video, let's do a recap. We can think of second-order linear PDEs with constant coefficients as having a coefficient matrix and a coefficient vector to store its second-order and first-order coefficients respectively. Linear transformations of variables transform the coefficient matrix and coefficient vectors in predictable ways. Using the eigenvalues of our coefficient matrix, we can determine what kind of equation we can transform our PDE into. This is the motivation behind categorizing PDEs into hyperbolic, parabolic, and elliptic categories. That's all for this video. Thanks for watching.